So welcome everyone to the Building Run Anywhere DynamoDB-compatible applications with Python. I'm Guilherme, I'm a solutions architect at ScyllaDB, and I'm always assisting customers to design data models that deliver the ScyllaDB's best potential. I'm a geek, self-passionate about Linux and open source software in general. I'm always helping family and friends to adopt open source software. With me, I have Nadav. Nadav, could you please introduce yourself?
Hi, I'm Nadav Arel. I'm a distinguished engineer at ScyllaDB. I've been working here for almost 10 years now and did a lot of things in Scylla, but in recent years, I've worked on Alternator, which we will describe today.
Thank you very much, Nadav. So for today's agenda, we'll cover the objectives of what we're trying to achieve during this presentation, what is ScyllaDB and an introduction to ScyllaDB Alternator. We'll review a sample application that can run anywhere. We will list the libraries used and talk about them, and then do an application demo and live demo for the application code. And then we'll look into ScyllaDB monitoring's insights. Nadav, could you please take away with our objectives?
Yeah, thank you. Okay, so what are the objectives that what we'll talk about today? So first I'll introduce ScyllaDB and Alternator, what these are, the capabilities, discuss things like monitoring, other things. And then we'll demonstrate how to write an application that uses DynamoDB API and run it anywhere, not just on AWS like you're maybe used to doing DynamoDB, but on any other cloud or on-premise or anything like that. We'll show a demo of how to do that, and you'll be able to run whatever application you want to run, also on Google Cloud, on Azure, Docker, whatever you want, and not just on DynamoDB. Okay, next slide, please. Okay, so what is ScyllaDB? So ScyllaDB is a database built for game changers. It's a drop-in replacement for Cassandra and DynamoDB, a NoSQL database. It has superior performance over legacy NoSQL systems. You can see also on the right all sorts of like compliments we got from InfoWorld, Forbes, places like that. We have better throughput at the same cost than the legacy systems, lower latency, and you can save a lot of on the total cost of ownership of your NoSQL database. And another great thing about Scylla is that it avoids vendor lock-in. So you can run ScyllaDB basically anywhere, on any cloud, on any private data center, even try it out or develop your application on your own laptop. We also have a database as a service that runs on Amazon and Google Cloud. So you don't even have to install anything if you don't want to. And Scylla is also available as open source. So that's an even better way to ensure you never have any vendor lock-in if you want to. Okay, next slide, please. Yeah, so this is just a few examples of the many clients that ScyllaDB has. You can see here various industries and companies of various sizes that probably heard of many of these. So these are some of the game changers that use ScyllaDB. Next slide, please. Okay, so like I mentioned before, we have the option, you don't have to install Scylla, although you can install Scylla, but you also have the option of a database as a service, which we call ScyllaDB Cloud, where you get this service. Right now, we have it on AWS and Google Cloud, but eventually we'll have it on other clouds as well. And you can get a fully managed cluster that you don't have to install or manage or care about yourself. We do it for you. We have 24/7 monitoring, support, response teams, everything you come to expect from a database as a service. It's secure. It's a private cluster. It's not like DynamoDB where you share the cluster with other companies that with ScyllaDB Cloud, what we have right now is that you get your own cluster and you're sure that you are the only one on that cluster. Yeah, we have multiple. It uses multiple availability zones, so the higher. I mean, to reduce the chances that any problems can reduce availability, can do geo redundancy, and you can choose from more than 20 instance types, so you can choose whatever performance you need or want, whatever fits your workload. Next slide, please. Okay, so that was ScyllaDB. Now, what is ScyllaDB Alternator? So when we started ScyllaDB, it was we started by being a drop-in replacement for Cassandra, and we supported Cassandra's APIs, which are CQL and the older Thrift. The CQL is the more interesting one. But what we added later was, we call it Alternator, is a DynamoDB-compatible API to ScyllaDB. And why did we want to add a DynamoDB API to the NoSQL database? So first of all, you can see that DynamoDB popularity is growing. It's very convenient to start with, and it's very popular Amazon. So people are using it more. You can see on the right a graph of the popularity of Cassandra versus DynamoDB over the last 9 years or so. You can see how it started with a very big difference, but now DynamoDB almost caught up to Cassandra. So we thought it would be interesting to also support the DynamoDB API. But other reasons why we wanted to do it is, first of all, ScyllaDB solves, with the DynamoDB API, it solves the real lock-in problem that people are using DynamoDB on Amazon and can't switch to any other cloud or a private data center or something like that because they don't have DynamoDB. Another benefit of ScyllaDB is now you can develop or run applications, DynamoDB applications, anywhere. So in the past, you couldn't, let's say you want to develop on your laptop, you cannot actually get, I mean, there is a DynamoDB local, but it wasn't really completely compatible with DynamoDB. So now you can develop and you can run on different setups. You can maybe, some of your customers want to do something on a public cloud, but others want to do it on a private cloud. So you can run the same thing on different kinds of clusters. And also another nice thing is the DynamoDB API is obviously not the same as CQL, the standard query language, but it's, in a lot of respects, it's close. So it wasn't like a big deviation from what we were already doing. So it fits nicely into the ScyllaDB, the DynamoDB API. Next slide, please. Okay, so although we have this name Alternator, it's not a different product. It's just a part of ScyllaDB. It's part of open source and part of the enterprise editions. And it just means that ScyllaDB will listen not just to CQL requests, but also to DynamoDB requests. You install it the same, just have to configure it with a few more options. You can see here, for example, you need to set up which port you want to listen on. And besides, I mean, in addition to having this feature on the software that you install, you can also get it on Scylla Cloud since June 2020. Next slide, please. Okay, so now a couple of slides on what's the difference between Alternator and DynamoDB. If you're already using DynamoDB, what should you know about the differences? So the primary goal of Alternator is to have full compatibility with DynamoDB API. That's the goal, and we want to support, if you already have DynamoDB applications, we want to support them either completely unmodified or perhaps you have to make some small changes, but it's mostly unmodified applications. And this should allow you to run DynamoDB applications anywhere that ScyllaDB runs and not be locked into Amazon, for example. And we are already very compatible with DynamoDB. We have a list of features that we haven't implemented yet. You can find it on our website, also in the source code, but also on the website, this compatibility.md file. It looks, here's a list of these things that we don't support yet. It looks maybe like a long list, but it really isn't. We have a much longer list of things we do support. This is just the things that we don't yet. Next slide, please. Okay, so other differences that you should know about is obviously, like Scylla, Alternator is a dedicated installation. You have to set up a cluster, either yourself or a managed cluster, but this is your own cluster, and it's not a multi-tenant service like DynamoDB. So the cluster you chose is dedicated to you. And another difference is that in DynamoDB, you don't even know which nodes exist. The client don't know how many nodes or which nodes exist. And in Scylla, you do. You have, if you have a cluster of 10 nodes, then you have these 10 separate nodes. So the client will have to send requests to all of them and not just one of them. So you need to do some sort of load balancing, and we'll discuss this in a few minutes. Another nice feature of Alternator and ScyllaDB is that we have a very powerful monitoring framework based on Prometheus and Grafana, where you can see a lot of different metrics and understand your workload's performance and get some insights perhaps on how you can improve this performance. Because yeah, it's not like unlike DynamoDB, where you pay just for the requests and you don't necessarily care about if it's efficient or not. Here you have the cluster and you want this to be as efficient as possible. And it's very interesting to see all the metrics and understand if something in your queries is not efficient and things like that. Okay, next slide, please. Yeah. So if you want to try Alternator yourself and see if your DynamoDB application works on it and I don't know, enjoy having your application run outside of Amazon or maybe even inside. So one thing you can do is just go to Scylla Cloud, ScyllaDB Cloud, and create a cluster. With a credit card, you can create a cluster of any size, but you can also get a free trial, like a small cluster, and play with that. And also another very simple option is just to run one Alternator node on your own laptop using Docker and with just these commands that you can see here. So you just have to pull the latest Scylla. This is the open source ScyllaDB release, and then run it with these options, which, for example, say that you want this to serve the request on port 8000, and the write isolation says how to handle concurrent read, modify, write requests. Okay, next slide, please. Yeah, so if you want to migrate your existing application from DynamoDB to Alternator, so like I said in the previous slide, you have to either install ScyllaDB or get a managed cluster on ScyllaDB Cloud. The next thing you would do is to tell your application to use the different IP address and not, I mean, instead of the normal endpoint, the address of AWS, you need to use the Scylla nodes, and we'll discuss this later when we come to load balancing. And if you have existing data, you'll have to migrate it from DynamoDB to ScyllaDB using some sort of tool that it can use the DynamoDB API, both to read the old data and write it into Alternator. You can use the same API, and we have such a tool called ScyllaDB Migrator that you can, for example, use or write some sort of migrator yourself if you prefer. Yeah. Next slide, please. Okay.
Thank you.
Thank you. I think, yeah.
Exactly. So we're here to discuss Python, right? So let's get into it. So first of all, let's discuss why are we discussing Python at all? So Python is a multi-platform and is available for almost by default on most Linux distributions. So it's just there. And it's a very simple programming language you interact it and learn. So it also has a huge list of libraries that are available. You can just install them with a simple command. And here in this workshop, we're actually using those libraries that you should use to run the Python application. And it also extensively used in data science. So it's a de facto option for you to choose when you're working with data science in general. And what about Alternator? So Alternator with Python, you can run your application anywhere. You can run it in any cloud provider, on-prem, on your CI/CD pipeline. So if you have your application test pipeline that you need to actually create a schema, communicate with the application, read some data from it, and then destroy everything, like in CI/CD pipeline, then Scylla can, as Alternator, can provide you that ability inside your full control. And you can also run it on your development machine, having the same exact features that it would have in a full deployment on a server. So it doesn't matter which option you choose to deploy, you always have the full access to full options. Performance will, of course, vary. So if you're running it on a dev machine or a CI/CD pipeline, it's different from running a full dedicated cluster, but you still have the access to every option that is available for you in any deployment option. So the tic-tac-toe example that we're looking at is a sample code that was initially written by Amazon and licensed under Apache 2 that we updated to use the Bodo 3 framework. And it works out of the box with Alternator. Bodo, the first version of the library, also works by default, but we wanted to bring some fresh air into this very classic project and show you how it can work with our Alternator functions just out of the box. And it is an online web multiplayer game, so you can invite your friends to play with you and just do some samples over it. And everything is using the database. So for every movement, for every query, for every refresh, the Python application is communicating with the Alternator database via the DynamoDB-compatible API in order to retrieve and write data to it. The code is available on the GitHub link on below, and it's also being on the chat, and will be sent to you after the presentation is done as well. So let's look at the application structure. We do have an application.py that is our main application file. The application is written in Flask, so this is a single application file that runs everything. Then we have a config file for you to point out configuration options if you don't want to present those via the command line. In this workshop, we're guiding you through running the command line option. So we're not actually using the config, but the config is there if you please to use it. Then we have a models directory with a game.py that actually defines a game class that handles every aspect of the game variables that are to be taken away with the actual processing of the game. We also have a DynamoDB directory which setups the DynamoDB connection, the connection manager, which handles the full lifecycle of the connection while the game is running, and a game controller, which implements all the game's logic. We also have some static files and templates that are used for the web things. So let's take a look at the libraries that we use. As I mentioned before, Python has a ton of actual included libraries. So we say it has libraries, Python has batteries included, but that's not always enough. So in this project, we use the Bodo 3 library, the Flask library, and we also use the ScyllaDB provided sample code Bodo 3 of Alternator Bodo 3, sorry. So the first library we're going to talk about is Flask. Flask is a micro web framework for Python. It does not require particular tools or libraries, so it just works with a single installation. It has no database abstraction layers, no form validation, so it has no incremental options by default. So you can always extend that with additional libraries that you can plug into Flask and make it interactive to interact with other libraries. We chose this library for its lightweightness and for its ease of configurability. So basically, this is like the tiniest web framework that we can use to write a web application. We also rely on Boto 3, which is an AWS provided library that is used to interact with AWS services via APIs. It is built on top of Boto Core, which provides the core functionality to access many of the AWS resources. It's important to remind you that as any AWS service, it's not restricted to DynamoDB. So Boto 3 actually provides you access to S3, EC2, Lambda, CloudWatch, and a ton of other AWS features. But obviously, for this specific workshop, we're focusing on DynamoDB API only. And then we have the Alternator Boto 3, which is the ScyllaDB provided. It is not actually a library, but it's some code in a file that you can import as a library. So it's a library in a file. It is a simple code that's built to create a resilient connection against an alternator cluster and have some workload balancing for connections against all the live nodes. It also has background live node detection, so it updates the list of live nodes while the application is running, so there's a thread there, and has connection balancing, so it will send requests to different nodes at every request attempt to make sure that not a single node in your cluster gets all the requests. We will circle back to this library in a moment. The code for this library is also available on the GitHub link, and it should be on the chat, and we'll also be sending you on the email afterwards. So let's talk a bit about the alternator load balancing. The alternator load balancing is important because when you deploy DynamoDB, DynamoDB is a fully managed solution by AWS. So load balancing is provided by AWS because you don't even need to point out an endpoint. The whole library just decides which endpoint to be connecting first, and from then on, AWS takes care of everything for you. As Alternator is a self-hosted or managed solution, and it's also composed of a multi-node cluster, and there is no leaders or main point of contacts, then it has presented you the load balancing flexibility. It allows you to deploy a load balancing between the client and the server, so you can insert a load balancer software in between those and make sure that it is handling all connections from your clients into your cluster, distributing connections accordingly. Or you can resort to client-side balancing, which is what we're looking at via this presentation. So Alternator exposes an API for checking cluster nodes. It has high availability workload balancer for the cluster nodes because it can tell you which nodes are live at the exact moment that it's consulted. And as you can see in the example of the curl I did here, it basically returns you all the IP addresses for the nodes that can be used to reach the Alternator interfaces. It also expects the ports to be the same throughout all of them. So the port is not informed, but it is assumed that you configure all the nodes with the same access port. The ScyllaDB Alternator is provided as a simple code. So it's just intended to provide you a simple code on how you can balance connectivity using the Boto 3 program. It also, as I mentioned, it checks for live nodes in a set interval, and you can also customize that. So every second, there's a background thread that is querying that live node, local nodes API, getting the list of nodes, and then updating the list inside the library in order to point out for the next connection that comes. It also updates the connection string in the background. So for every new request, it's going to send the request to a new node. And it has a random selection of nodes. So when you look throughout a histogram over some time, then you see that all nodes receive an average of the same connection and count. It also actually ensures that the only live nodes are tried. So if a node actually leaves the cluster, it will leave the local nodes list, and then Alternator API will not connect to the single specific node. It is also important to remind you that if you're used to working with CQL, this driver is not token or shard aware. So if you have more than 3 nodes, for instance, or if you have a different replication factor other than 3, then the node that is receiving your connection is not guaranteed to be the node that will actually have a copy of the data. So let's say you have 6 nodes, there's a 50% chance you might or might not hit the node that actually has the data, but that's still extremely performant. So let's dive into the code. Let me share my secondary screen. Okay, so the first code that we're looking at is the application code itself. So it's, as I mentioned before, it's a Flask library application. So it basically imports every model from the library itself. So it uses render template, request, session, and many other options that are used, offered by the Flask API. And it relies on the previously mentioned model for the game and the DynamoDB connection manager and controller, and also for the DynamoDB creator that will create your logic on the background. Then we instantiate this application and make sure that we set a debug and secret key to be a random string every time that the application is started. And we parse some application command line arguments or configuration file entries. So in both cases, you can, or the third option is environment variable. So command line arguments, configuration file, or environment variables, those three options are available for you to configure the application. But as I previously mentioned, we're always using the command line options here because that makes things simpler. But if you actually want to make an application that relies on environment variables for configuration, for instance, you can use that. Then we instantiate the connection manager and controller based on top of it, and we start the server using the provided server ports. After that is done, the server is running and active. Then we export functions that will actually latch onto routes when you access the application. So for instance, when you access the application logout, it will actually redirect you to the logout function that will queue the session for the specific user and then return you to the index. We also have functions for creating a table. So if the table is missing upon the first start of the application, you can use this function to make sure that the table is created in the background without resorting to command line options. We also have an index function that will actually draw the index file that will bring you the three tables. Those three tables are the pending invites for the user that is looking at the application. So you can join or reject games that are pending. You can also see the table status, which are for the active games that are still running. You can see those and rejoin them if you miss them. You also have a historical view of all finished games, so you can see who you played against, what is the time, and what is the actual result. So if you won, lost, or tied against that specific game. You also have functions exposed to create a game and actually make sure that you reach a play state where you'll be redirected to APIs that will interact with the database in the background and access game data and refresh your screen every time you're playing. And also an API that will provide you a game via the game ID and give you an access to the board status, what are the already played spots, and what are the next turn. So who user should go next. All of that's provided as an API. So you can see here that we gather information on the current play, and then we build a JSON file and return it for the play.html template. So everything gets stored in the database, transformed into JSON, and pushed to the browser for the play.html profile file, sample file, with a JSON template that will be expanded into every variable that is using that page. The game data itself is an API that is continuously queried by the application while it's still playing to make sure that nothing has changed on the board. If there is a change, then there's a JSON response to what is the new status of the board, and the browser can just refresh the status of the screen and get the player to the next play state. We also have functions to accept and reject games. So when you're looking at an invitation, you have the accept and reject buttons. Those two buttons will get you to a page that has a form, and the form will submit a request to the API, and the API will accept or kill your game request. There's also functions for selecting squares. So every time that you click on a specific square in your board, there's options of who is calling that, what is the user, and what is the game ID. And from that, the game can infer if you're a cross or a circle. And from then, it will commit that against the database and return to the player. So this is the main application file. This is the whole web logic that is implemented throughout the game. We also have the model of game.py. The game.py, as I previously said, implements a class game that has every attribute that is handled via during the application lifecycle for every aspect of the game. So it stores the game ID, host ID, opponent ID, what is the status date, what is the opponent user, and whose turn it is. And it also exposes some methods to get status of the game. So is the game in progress? Is the game completed? Is it not accepted yet? Get the date that the game was created on. So there's a string called the status date that has the status underscore and the date. And this string basically splits that function splits that into two and returns what is the game that is the date that's stored in that string. You can also compare two different games if there's the very same object. Get the opposing player. So from a player that is looking at the board, you need to know who is the other player, but the information that is stored in the database is the same for everybody. So there's internal logic to see if you're the same player, you're the hosting player, or if you're the opposing player, and then return what is the other user. And finally, we have a get result. So that will check whether the game has actually finished or not, and then get you whether the user that looking at the state won, lost, or tied against the other user, and the same for both of them. We also implement on the DynamoDB directory a setup DynamoDB, which is a file that will import the Bodo3 alternator that we mentioned. The get DynamoDB connection is instantiated when you're starting your application, and you provide an endpoint or an endpoint list, and that endpoint is exploded into a list or create a list of a single member, and then it gets passed on to the setup2 function of the Bodo3 alternator library in a file. That specific function is what will override the Bodo3 configuration and make it able to connect to multi-hosts according to the logic that is implemented here. And after that is instantiated as an endpoint, then we use the endpoint to point to the endpoint URL while we're instantiating the Bodo3 resource option. So we basically provide that we're instantiating a DynamoDB resource, then points to the endpoint URL that we're going to use throughout this usage, which we just created. Then we provide an AWS secret access key and access key ID, which have to be provided even if empty, but the library won't work with those are not there. So you need to provide anything. If you're not enabled authentication or alternator cluster, this won't matter. If you did, then you should provide the correct user and password combinations. And region name actually is required by the library, but can be anything because alternator has no regional setting. So you can just point everything you want here. The rest of the functions are not actually used for this run because we're running on local mode. So all of this is used by the code to communicate with AWS instances. If you want to do tests against the actual DynamoDB instance, you can use that here. Also, we have a create games table function that is used to instantiate the table if it's not there. As I mentioned, it should be created on the first run, but if it's not there, there's an API on the web that you can use to trigger the game creation, force it, and it will just call this function. This function instantiates the database connection and then calls the create table function to create the table named games, provides a key schema of an attribute name called game ID, which will be our primary column or partition in partition column, as if you're familiar with working with Scylla, and the key type, which is hash. So it will be a hashed string. The key definitions that we forced are we're using a game ID. So the game ID is our primary key. Then we also have a host ID, which will be type of string, a status date, and an opponent ID of type string. I have to define these attributes because later on I'll be creating global secondary indexes on top of them, and they need to be previously defined as attribute definitions before I actually get to create a global secondary index. Then I have to provide a provision throughput, otherwise it won't accept the table creation. Alternator has no concept of actually enforcing provide provision throughput, but you need to provide those to get the library working anyway. So in here, I provided a 1 and 1 for read and write. In other places, I provided different values because that won't just apply on Alternator. Then we get to this global secondary indexes creation. Global secondary indexes must always be created when you're creating a table. So it's important that you define those at this very moment. So we created an index name host ID status date that's based on having the host ID as the partition key or the very first primary key, and status date as a range key as a sorting column. So it will be partitioned by host ID, and for every host ID, there's a secondary column. If you're used to work with Scylla, that will be close to a clustering column. So host ID is your partition key, status date is your sorting column. The projection, so you need to state exactly how many attributes you want to be copied when you're using the index. As this application relies on every information being on the index, then we need to provide the projection type all, but your mileage may vary depending on what you're trying to achieve. And then the provision throughput, the same as I mentioned before, you can just input any value here and it should work. Also, we have another secondary index that's opponent ID by status date. So opponent ID will be the primary key for this specific index, and the sorting key will be status date. And we also provide the same projection and provision throughput information as we did before. So this should create a table, wait a few seconds, and then return an object, the games table, and that will be referred to throughout the whole game execution as a game table. After that is done, then we have a connection manager. The connection manager is a class to actually manage the connection of the whole application while it's executing. So if the mode is local, it will just call the get DynamoDB connection and inform every option that it has via its execution, and set up the games table. The setup games table will basically recall for the create games table if it has not been created yet. So it just makes sure that the table is created and returns an object that is the game table reference throughout the whole execution. So it can be just reused as an object. And finally, we get to the game controller. So the game controller is our main logic implementation of this application. Then we have a create new game. So this create new game will basically insert or put an item into the database. The database has to inform what is the table name and what are the item attributes is going to be inserted. So it will insert the game ID, the host ID, the status date, the creator user, which is the host ID, the turn, which is the next person to play, which is by default always the person that is being challenged or the invitee, and what is the opponent ID, which is the invitee's name. Then after it's inserted with a pending underscore and now as date time, then the game is created and the user can accept the game. So the accept the game function queries if that doesn't update when there is some certain conditions met. In this case, the status must be, the target status will be in progress, and it's expected for the game to be of an to have the status date column attribute to have the value list pending beginning with. So it should begin with pending underscore and the date. And if it matches, then the put is executed, which is the attribute update. So you can see that the status date will be put as the value of status date. The values of status date we just instantiate here as a status, which is the in progress, plus the date. So it will ensure that the game moves from begins with pending acceptance to in progress. So the user has just accepted the game and we'll start playing now. You can also reject the game invite. So in this case, there's a key, which is the game ID. Then the expectation is that the game should be in a state where it begins with pending. And if it's in that state, then we execute a delete item and the game is just removed. So this is for simplicity. You would probably take another option, different route if you're implementing this in production. But as this is just a sample game, that's how we decided to demonstrate how a delete item would be used. You also have functions to query database. So there's a game invites function to use the database by an index. to get the opponent ID and status date, then do a key condition expression where you filter this data based on some attributes. So the key of opponent ID should be equals to the user, so the user that is looking at the game, and the key status date should begin with pending. So the query is executed in the database, the data is stored and returned back to the user and then sent back to the web page. If there is no games, then the game list is just appended up until 10 items. So basically it just shows you 10 of the games. You also have the core logic here, which is the update board and turn. The update board and turn will get the game and what is the play that is being tried. So, and what is the current user that is doing the change. So it will create some logic and make sure that the update is executed when the game begins with in progress. So the state must be in progress. And the turn is the actual current user. So you can't play someone else's turn. And the position doesn't actually being filled in yet. So there's an attribute per position. So for every square in the game, there is a position attribute. And if that attribute has been filled in, then the update doesn't work. And the game just returns that this display is invalid. So the core logic, it's just relying on the comparison of the attributes that is stored in the database with what are the user trying to do. There's no additional logic to be implemented here because the database takes care of everything being communicated correctly between the database and the application server. There's also functions to get the bird state. So it shows me what are the pending games, what are the pending squares, the fielding squares, what have been selected for them, and also check for game results. So this is also some of the core logic to make sure that if you have 3 items in sequence, then it gives you the win or a lose or a tie. So that core logic is implemented in this function. Also, the check for tie. So if you can make sure that if there's any place left and the previous result has not returned it, then there must be some available play. If it's not, then it's a tie, and it's a tie for both users. And you can also change the game to finish state. So this function will actually check if the game has been finished. And if it has been finished, the last play has been done, then the game is updated to have the updated user to finished. So the status will be changed to finished. The last player to be played will be recorded, and also the status date will be updated for the finished and underscore the status date. And some merge query functions as well. We also have the game use status. So this will actually be used to fill in the tables on the index. And this is used to get the host games in progress. So I can look at the games that I'm involved and they are in progress, and the games that the opponent is being ran and also being in progress. So it uses both indexes to query for the host ID and status date, or by the opponent ID and status date, and join them into a single queue that will just be displayed on my index. So, okay, that's all nice and done, but we haven't seen the application yet. So let's take a look at it. Let me share my full screen now. All right, so let's go back to my terminal. So as I previously mentioned, we're using the command line options here to start the application and provide parameters to it, instead of just relying on configuration files or environment variables. And in this case, I'm calling the Python 3 application.py and providing a mode of local, because I want this to communicate with endpoints I point it to, not with AWS services, which is the default that it would do. And then I will provide an endpoint list. In this case, I have a 3-node cluster that is running on my machine. Let me actually show you that. So, oops, it's harder to actually get them all on the line. So I have 3 nodes composing a cluster in my own computer. So just to make sure that you guys understand that you can run a full-fledged cluster in your own computer, your own development environment, and still have the full functions that you would have on your live or full deployment on a server. Then I provide the IP addresses for 2 out of the 3 nodes in that cluster, and my application is started. What application does is, as it's calling for the DynamoDB Alternator library, it's printing this picked message. So every time it's picking a new server, it's printing to me just so I can show how is it actually distributing connections between the live nodes. So in this case, just before it gets started and actually says that it's serving, it's already picked one of the nodes. Then for the next connection, so checking for if the game table exists, if not, I'll create it. Then it picked another replica out of the cluster, and it's just continuously do that while the application is running. So your connections are all balanced. All right, so after applications is started, then I can show you, I have two windows here where I have not logged in yet. So let me log in on this side with the user A. So I'm logged on here, and I have no pending invitations because it's a brand new installation. So I'll just create a game, and I'll choose my opponent as B, which is will be my secondary window. After I just create the game, I can come to the secondary window and log in as B. So I can see that from my first user, my status is still pending, and it's the B's turn. So I go to the secondary window, and I have a pending invitation from the user A from this timestamp, and I have options to accept or reject this game. So when I click on accept, then the status is updated to in progress, and I can start playing. So this is B's turn. So B is the window on my right-hand side. So I just start playing. The opposing user always starts with an X. So the X is just always your opponent. So from the one that created the game. So the updated has been, the play has been updated to both windows. We can see that the game is in progress, and it's A turn now, which will be a circle. So I use the A to put a circle, and then it's B's turn again. And I'll just keep playing up until I have a result. So let's say how things are going. And then, oops, sorry. And then you see that circles, there's 3 circles in a line here. So I won and B lost. So the game has been moved to a finished state, and now it's kind of archived. So if I go to my main screen, I'll see my recent history listens the opponent and the result that my game. So this window here is for the user A. I challenged the opponent B, and I won against him. And from this window where I'm logged on as B, I can see that my opponent was A, and I lost this game. So this is just to show you guys how it all works. I just reminded that I had not exactly showed how a invalid play works. So I think that's important. So this is B's turn. So I do my first game here, and from A window, I try to do a play that has already been done or not allowed. Then you select the square that's not in your turn, or the square is already selected, or the game is not in progress. So it is in progress. So basically it's telling me that I'm trying to make a play that I'm not allowed here. If I go back to my main screen, I still see that games in progress has a list. So there's a pending game here, which I can continue playing. And there's no invites has already accepted the game. So this is all being stored in the database. There's no caching between my browser and the application. Every call for it's reaching the database and returning data. And if I look at my, let me just exit the game window. It keeps just refreshing. It's the local host, so everything is so fast. But you can see that for every request, it's printing a picked message, and the picked message always points to a new IP. So this reached the 3 node, this reached 2, this one reached 4, and so forth. So every connection. So here on a single call, it got as it got to the index screen, it makes a lot of calls in the same load. And for every call that was done on the backend, it reached the new server. So all of these connections were balanced among all the nodes. So let me go back to sharing the presentation as I finished demonstrating you guys the actual gameplay. All right. So that's all fine, but okay, so what can we extract if we're monitoring this whole stack? And this is where Scylla monitoring stacks comes into play. Observability in Alternator is provided by the Scylla monitoring stack, which is provided by Prometheus, which is always in the background collecting metrics from your cluster and storing it for a historical period. Also, you have a Grafana instance for visualization, along with a lot of nicely done Grafana dashboards. So Scylla provides you the dashboards and a set that you can use to visualize and extract information and extract value from the data that Prometheus collected in the background. And also on top of that, there's Alert Manager and Alert Advisor and Loki, which are accessory projects that runs with Grafana and Prometheus to provide you additional functionality. For that, there's a recent webinar on observability that you should look into. You should have on our blog pages, but I really encourage you to take a look at it. It's really nicely done presentation. There are hundreds of different metrics that have been collected. So all of those metrics can be historically checked. So you can go back to a week ago, a month ago, depending on the data retention, and make sure that you troubleshoot an issue that you had in your application, your whole environment. There's types of counters, rates, histograms, and also advisory dashboard that shows you whether a manager is offline, how many timeouts you had. That's like a live instant and not historical data. And also you have the total per data center, per cluster, per node, and per shard. So you can have different levels of granularity of visualization, where you can look into many detailed information in each of the panels. So let's say you detected one spike, and you can look into the shard level, which is a CPU level in Scylla, to make sure that you track down what is going on with that specific point in time. In this case, this is a YCSP write only stress. And we can see that this is a 3-node cluster with no unreachable, no joining or no leaving nodes. And each of the 3 nodes is reaching 100% CPU utilization. So you can see the spike going up and staying like that. And also there's how many DynamoDB APIs requests being for each type. So you can see that there are get items and put items. Get items are zeroed, but you can see that put items have close to 25,000 operations per second being executed. So that is done via the dashboard itself. And you can also have the entire per cluster, which is the chart just below. So put item by cluster. And then you can see that cluster-wise, it reached almost 80,000 operations per second with a 3-node cluster, just for writes. In addition to the rate of operations, you can see also the latency for each one of them. So you can also see, again, the count of the operations being done, the average latency for the actual function being called, and then the 95th percentile and 99th percentile latencies for that call. So let's say I have a put item slow down in my cluster. I can go back in time and look at which node was faulty and which starting that node was faulty. How was my whole cluster doing, for instance? Or when I deploy a new application, how is it being performed? How is it using my cluster? Also, we have a very nice large items detection screen where you can find large cells, which is basically the whole combination of all attributes in your DynamoDB row, and also a large partition. So when you have many items in a single partition being clustered or sorted with your sorting column, it can sum up, maybe every line is not that large, but they all can sum up to a very large partition size. And you can always use this information here to track down and hunt those problematic patterns in your usage, in your application. So just before we go to Q&A, I'd like to raise a quick poll. So just for a sense of scale, we'd like to understand how much data do you have in your under management of your transactional database systems. It may be under a terabyte, 1 to 10 terabytes, 10 to 100 terabytes, or over 100 terabytes. I'll give you a couple more seconds to respond. You should pick the answer that best matches your current data set, but feel free to not respond at all if you actually don't mind participating. All right, I think that's it. So for the Q&A, let's see if I do have pending questions.
Yeah. Do you want me to start, maybe?
Yes,
Because
please.
I looked, yeah. Okay, so it looks like we don't have a lot of time for the questions, but remember that, I mean, you can find on our site a lot of documentation. Also, you can contact us. We have a Slack channel. We have a mailing list. You can ask us questions also after this presentation. So, okay, so let me start with one question from Jen. The question is, I understand that the webinar focuses on the differences between Scylla and AWS or Google Cloud, but I'm also looking at Kamatera. If there's time, is it possible to discuss those differences as well? So if there's one thing you should take away from this presentation is that Scylla allows you to run the DynamoDB API basically everywhere. Anywhere you can get physical machines, virtual machines, and so on, you can install Scylla. And it's not only on Google Cloud and AWS. You can do it on any other cloud or any other even physical data center that you have, or whatever setup you want. So what we do differently on AWS and Google Cloud is that we also have the managed the database as a service. So you don't even have to install anything. You can just get a managed cluster from us. But on other clouds, you can also run Scylla just the same. You'll just need to install it, I mean, yourself, and it's not a managed service. So okay, so that's that question. Guillermo, do you have something you want to answer?
Sure. Could you please speak a little more about global secondary indexes and their usage, please? So Jen, global secondary indexes are additional indexes that you can use to query your data by as if it were a partition. So in that case, let me go back to the slide. I think it makes more sense. It's not flashing the slides in my presentation. Let me quickly share my code here. So in this case, I don't have a gain by ID here. I'm just using the host ID and the status date to query by it. So this allows me to query all the data that's being stored by host, which is an attribute in your main column. So this is just another way of actually exposing a column that is not your primary one for you to query just by it. And it's very performant because it replicates data when you write to it. So it's replicates data when it's written to. But when you read it, it's just a single operation. So it's just a virtual table that is you're just reaching and extracting this information. So it's also very performant. And this is exactly what is the recommended use. We do have a lot of further questions, but I think we don't have time to go through all of them. Thank you, everyone, for your participation. And I think that's very awesome to respond to those. If you also wants to follow up with those questions, please email them to me or to Nadav, and then we can just start replying to you guys. Thank you all. Thank you for joining us.